Swayam Prabha. Digital India. Educated India.
Good morning. We have already talked about dimension reduction in two ways. One is using PCA, another using random projection. In today's class, I am going to be talking about randomized projection or random projection method. Earlier, we introduced the notion of random projection. We introduced the notion of random projection using concentration of measures. We introduced the notion of various inequalities. We showed that if we can compute and quantify the moment generating function based on the bounds in the moment generating function, we can translate them into probability tail inequalities, tail probability inequalities. In that context, we introduced the concept of sub-Gaussian, sub-exponential, chi-square being sub-exponential, it's sub-exponential. We derived the concept of embedding using random projection. Today, I am going to talk about an alternative path, a little bit more straightforward, much more from the basics, and also talk about various variations of the choices of random projection matrices. So, in summary, dimension reduction can be obtained using deterministic method, using randomized ideas. Deterministic methods based on PCA, this is a random projection. I am going to concentrate on the method of random projection in today's class. To that, I would like to be able to introduce the problem. I know you have already been introduced to this problem, an introduction. Let X be a finite subset of vectors in Rd. D is the dimensional of the space. D is large. The goal is to find a mapping from the set X, which is a subset of Rd, into Rk. K is much less than capital D. You may remember we have used different symbols for the dimensions, sometimes little d, sometimes capital D, sometimes m and n. I don't think that should bother you. So, we are interested in mapping a set of finite points in a high dimensional space to a set of n points in a lower dimensional space. We have called this embedding from high dimensional to lower dimensional. We have also seen in trying to do the embedding from high to a lower dimension, we may not be able to preserve many of the properties. One such property that we cannot preserve is pairwise distances. If there exists a mapping that can preserve the pairwise distances, is called isometric embedding. When going get tough, we always compromise. So, we are now going to be talking about near isometric embedding through random projection. So, f is a function that maps Rd to Rk. I am interested in the images f of xi, where xi belonging to the capital X. You can think of capital X to be a matrix where the dimension, the row dimension is 1 to capital D, and there are n points, there are n columns in X, and that's what this one is. Pictorially, X is a subset of RD. Xi is a typical member of the subset. Yi is the image of it. I am interested in the properties yi is equal to f of xi. One property of interest is the preservation of pairwise distances, pairwise Euclidean distances. You already know that we can consider distances in various measures. Right now, we are only going to be concerned with Euclidean distances. A map is said to be isometric. This may be a little bit of a repetition, but it's worth it. The distance between the original objects in RD is the same as the distance between the images in RK. Isometric embedding is feasible when K, the target dimension, is greater than or equal to D, but for K less than D, the best we could hope for is near isometry, where the distances are approximately preserved. Yes, there is an overlap in this, but it is worth doing it. Now, I would like to be able to introduce a new concept called a function f RD to RK. This is the vector valued function of a vector. That means the input is a vector, the output is a vector. The input is a d-dimensional vector, the output is a k-dimensional vector. Such functions in mathematics are also called maps. Please remember, one can consider three types of functions: scalar valued function of a scalar valued function of a vector valued function of a vector. So vector valued function of a vector, otherwise is also known as map. We call this map a Lipschitz map. I'm sure you all have heard of Lipschitz condition, when you derive conditions for the existence of solutions of ordinary differential equations. So when do you call this function, which is a map? So map is a technical term to denote vector valued function of a vector. For uv belonging to x, there exist constants a and b such that the square of the distance between the images is less than or equal to a constant multiple of the square of the distances between the original, is also greater than or equal to a constant multiple of the square of the distances between the square of the distance u minus v, which is the difference of the two vectors u and v. That means so long as the constants a and b are manageable, if b is not too large compared to 1 and 1 is not too much below 1, you can say distances can be approximately preserved. Please understand, this gives you a clue that we may need to realize the map that we are looking for from RD to RK as a Lipschitz map with the appropriately chosen constants a and b. B is a constant for the upper bound, a is a constant for the lower bound. So method to realize this Lipschitz map is not easy. In general, it's not easy. In here, we are going to define a random projection that's going to take the place of the function f. That means we are going to realize this Lipschitz map function as a random projection matrix. Again, just to recall, projection matrices are orthogonal projection, oblique projection. We have already dealt with in the context of modeling least squares. Here is a third type of projection. It's called random projection. It's called random projection. To project means I'm going to bring an object from one space to another space. Random means the design of the map depends on random elements. That's why it's called random projection. So it is shown that the map f that approximately preserves the distance can be realized as a linear map, and such a linear map is going to be a random projection matrix. So that whole thing now comes into play. So random projection, that's what I'm now going to describe. Let X be a subset of RD. That means X is a matrix of size capital D by N, where the n elements are the columns of the given data matrix, where D is large, K is the dimension of the target space. I don't think there should be any confusion. I use capital R to denote the real number. Here I am also going to use capital R to denote the random matrix R. The juncture will tell you which one we are referring to. So let capital R be a matrix of size K by D. That's a linear transformation. This linear transformation maps RD to RK. And this must be realized as a Lipschitz map. And we also require this to be a near isometry. Near isometry means what? I would like my B to be 1 plus small number. I would like my A to be 1 minus a small number. That means A and B are not too much different from 1. Slightly above. B is slightly above 1 and A is slightly less than 1. So let this be the input matrix. Let this be the output matrix. Please understand, Y is K by N. This is D by N. The number of objects remain the same. The dimension gets reduced because K is much less than D. Our objective is to quantify how small K can be in order to be able to achieve near isometric embedding. So I'm going to express Y as R times X. So K by N is equal to K by D, D times N. Please understand, this is a much more direct approach. The earlier approach, it was a slightly indirect approach. We used the notion of concentration inequalities, using which we defined sub-Gaussian, sub-exponential, and derived the random projection as a corollary from the theorem on sub-exponential. That's one way. Now I'm trying to introduce a much more direct way without having to invoke some of those ideas. Of course, we will come back to concentration inequalities again. The proof of near isometry relies heavily on the concentration of probability measures. And to that end, we will also use Chernoff bound. So it's a direct use of Chernoff bound to get tail probability bounds. And this is much more a direct method. So R is Rij, I running from 1 to K, J running from 1 to D, maps the vector Xi in Rd to Yi in Rk, where K is much less than D. When we realize F as a linear map, it is computationally simpler to implement. Hey, that's a key thing. We can have the cake and eat it too. I need to perform the transformation without having to work too hard. Linear transformation comes to the rescue. And in so doing, I want to be able to preserve the pairwise distances to as nearly to isometry as possible. So let X represents a configuration of data in Rd. Y is embedded configuration in Rk. Our goal is to preserve the local separation approximately. Why are we interested in pairwise distances again? Many of the properties in data analytics examine the similarities between objects. So I would like to be able to, and distance is one measure of similarity, so I would like to be able to preserve the pairwise distances as closely as possible. So two questions arise: how to pick the elements of the matrix R, and prove that such a choice can indeed realize the near isometric embedding of X in X from Rd to Rk. The choice for the matrix, there are several. So there are various choices for the elements of R. At least there are well-known three distinct choices. So Rij is a typical element of the matrix R, I running from 1 to K, J running from 1 to D. There are three types which are very popular in the literature, in the early literature. Again, this early literature began in the early 90s, so it's hardly 30 years old, at most 30 years old. That's it. So first choice is, I'm going to call it type 1, type 2, type 3. In type 1, Rij are IID samples from standard normal. So if I have a matrix R, which is K by D, if I am going to, this is K by D. If I have a vector, an object U or Xi, I'll call it Xi. This is D by 1. If each of the elements of the rows are normal random variables, they are all real. So I had to perform an inner product with the ith row on this vector. So it involves multiplication and addition. Multiplication is more expensive than addition. So people who came a bit later, they wanted to improve the efficiency of the implementation of the IDS. It is with respect to this improving efficiency, the two other types were suggested. So the first one is Rij is going to be plus or minus 1 with a probability half-half. What is the beauty of that? The ith row now consists of, ith row of the random matrix consists of plus 1 minus 1. Multiplying by plus 1 minus 1, I don't need to multiply at all. So I need to add all those quantities corresponding to plus 1. I need to add all those quantities corresponding to minus 1 and then subtract the total sum, the total positive quantities and total negative quantities. So this one is computationally very efficient because I do no multiplication. But in the type 1, I need to do multiplication and addition. So you are saving ton of time in multiplication. So that's a big saving in itself. Then there is a third choice. If I can choose the matrix R to be sparse. Now, I want you to be able to look at dense versus sparse. A matrix is said to be dense if the total number of elements is proportional to the square of the size of the matrix. The total number of elements in an n by n matrix or m by n matrix is either n square or mn. So if I can make sure a large fraction of the elements are 0, multiplying by 0, it doesn't take any time. So Rij is, it takes the value 0 with a probability 2/3. It takes the value plus or minus square root of 3 with a probability 1/6. In each of these cases, this is something extra I'm trying to do. That's why I'm trying to do this in a separate module by itself. So in either case, you can verify the expected value of Rij is 0. The variance of Rij is 1. So if I can induce the same moment properties for Rij, much of the proofs of earlier types can in principle be carried over to the later types. So I would like to be able to preserve the conclusions. So look at this now. I would like to be able to preserve the power of the conclusions while at the same time trying to reduce the cost of computation. That's the idea. So type 1, type 2, type 3. The random matrix are said to be of type 1, type 2, type 3 if Rij's are of type 1, type 2, type 3 respectively. The action of R is defined as follows. Now I'm going to define how I'm going to use the random matrix to define my map. So V is equal to F of U. So that means this is RD, R capital D. This is RK. This is U. This is F of U. this is f, and f is going to be, f of u is going to be 1 over square root of k or u. 1 over square root of k is a kind of a scaling factor that's meant to induce certain properties. Now look at this now. U is a deterministic quantity. F as chosen by Ru is random. So V is random. So even though U is deterministic, V is random. That is, the D vectors in X are mapped onto K vectors in Y. And Y is called the random projection of X. So the collection of all members of X now become members of the collection Y. So Y is the image of X, and that's what's called. Y is the projection of X. Y is called the random projection of X. Now I would like to be able to talk about the properties of this random projection. Let R be a K by D matrix with its elements being IID random variables with zero mean and unit variance. Please understand, we only need to use first two moments to start with, even though if it is type 1, it's Gaussian. Then the map f from Rd to Rk is defined by f of a is equal to 1 over square root of k Ra, where a belongs to the host, the original space Rd. So f of a is a random vector in Rk whose components, now look at this now, a is fixed, a is deterministic, R is random. Elements of R are IID random variables. They are mean zero, variance unity. Now, in trying to compute, so f of a is a vector. In trying to compute the ith component of the vector, I am going to take the ith row of R and multiply it by a. So the ith component of the vector f of a is going to be linear combinations of IID random variables, each of which have mean zero and unit variance. X of R, the scaling factor 1 over square root of k. So f of a is a random vector in Rk whose components are IID random variables with mean zero, variance 1 over k times the square of the norm of a. And that is the expected value of the square of the norm of that is equal to square of the norm of a. Look at this now. I have a vector in Rd. I have an image in Rk. This is a, this is f of a. This is deterministic, this is random. So what is it we are trying to say? The square of the norm of the image, the expected value of the square of the norm of the image is equal to the square of the norm of the original object A that is being mapped. So that's the proposition 1. I'm going to give you a quick verification of that. Let R superscript I be the ith row vector of R, because ith row vector is something that is going to be doing the operation on the vector A to get the ith element of the output. So I'm interested in inner product Ri with A. I'm going to call this a vector C. The output is a vector C. So Ci is the ith component of that vector C. So C as a vector is f of a is equal to 1 over square root of k Ra. We already know Ci is equal to the inner product of that. So expected value of Ci, the ith component of the output vector, is 1 over square root of k summation expected value of this. Each one of these are IIDs, mean zero. Therefore, A comes out, expected value of Rij, that is zero. So the output is such that output is a vector whose components also, while being random, inherits the mean zero property. Now I'm going to compute the correlation between, or covariance between Ci and Cj. Please understand, C is the output vector. So Ci is computed from the inner product of ith row Cj is computed from the Ri, this is Rj, this is A. Therefore, if you substitute, you get AMAL times expected value of RIM RJL. That's very easy to be able to verify. I first do this, then I do this. I substitute, I take the constants out. Expectation of the sum is the sum of the expectations. And these are IID random variables. Expectation of the product is product of the expectations. Each of them are mean 0, so that is 0. So for I not equal to j, expected value of Ci Cj is 0. That means the output vector C is such that the components are mean 0, they are uncorrelated. Now I am going to compute the variance. Please understand, Ci is a random variables, they are mean 0. So the variance of Ci is essentially expected value of Ci square. This is equal to 1 over k times, this is the, you remember the scaling factor 1 over square root of k? Square of square root of k is 1 over k. This is summation j is equal to 1 to d aj rij whole square. So just like a plus b whole square, a square plus b square plus 2ab. So there are second degree terms, there are cross terms. The cross terms, just like in here, they involve RIL, RJM, they are independent, mean 0, so the cross term becomes 0. Cross term becomes 0. And we already know the variance of the individual components are 1. Therefore, this expression now reduces to 1 over k summation j is equal to 1 to d aj square. And that is equal to 1 over k times the square of the norm of A. Square of the norm of A. So, expected value of the square of the norm of A is equal to expected value of norm of f of A square, which is equal to expected value of Ci square, which is equal to expected sum of the expected value of Ci square, which is k times, because each of these terms are each of these terms of the summation are constants. So this k times 1 over k this, that's equal to square of the norm of A. This result holds good for all the 3 types of matrices described above. Look at that now. I'm killing more than one bird in one stroke. So what is that we have proven? We have proven that the expected, so let's go to the property, the claim in the property. Is an important proof, is an important result. That's why I'm trying to spend some time. So if I picked my f of A to be as an equation phi, equation 6, what does this tell you? A is not random, f of A is random. F of A is a vector. Therefore, its length is a random variable, square of the length is a random variable, therefore it is expected value. So expected value of the square of the length of the image of A is equal to the length, the square of the length of A itself. So in an expected sense, this mapping has not distorted the length of the given vector too much. I shouldn't say too much right now, but in an expected sense, f of A image, the square of the length of f of A is the same as the square of the length of the original vector A. Please remember, f of A is random. Even though it is random, its expected value is the same as the square of the length of A in the original space. If a random quantity is such that we already know in the context of concentration of inequalities, the probability density tries to heap itself around the mean of it. So that's the idea that we are trying to work towards. So F is a map as in property 1. Let A be in RD. Now, instead of assuming any vector A, I'm going to normalize the length of the vector in RD. So let A be a unit vector in R capital D. Then square root of K, F of K, please understand, F of A is equal to 1 over square root of K RA. Therefore, square root of K F of A is equal to RA. It's a random vector in RK whose entries are IID random variables with the mean 0 in unit variance. We have already talked about that in the context of property 1. I'm trying to reinforce it by stating it again. So now remarks. The matrix R, which is D by K matrix, may have a non-trivial null space. Please understand the following. That's very important. Suppose A is a matrix which is 1, 2, 3, 3, 2, 1. So here K is 2, D is 3. So if you consider a vector X such that belonging to R3, AX is equal to 0, that implies X belongs to the null space of A. That means the null space of a matrix X is a set of all vectors that annihilate the vectors in here. So I am working in R3. The rows of A, they span only a 2-dimensional subspace. So 2-dimensional subspace in a 3-dimensional space, you can think of it as a plane. So there exist vectors that are perpendicular to the plane, whose inner product with vectors in the plane will be 0. So if I say AX is 0 means what? X is simultaneously perpendicular to the first row and the second row. First row and second row define a subspace, which is a plane. That means X is a vector that is perpendicular to the plane. So if I am working in a 3-dimensional space, if I consider a 2-dimensional subspace, there exists a 1-dimensional subspace that is orthogonal to the 2-dimensional subspace defined by the 2 rows of that. That's the notion of a null space. Now, my matrix R being K by D, and K is less than D, much like the above example, there must exist a non-trivial null space of R. That's what is talked about in here. So hence the points in X cannot be arbitrary. What does it mean? If the selected set of points X, they fall in the null space of A, they will all be mapped to 0. If they will all be mapped to 0, then I cannot preserve pairwise distances. So we tacitly assume that the given subset are not totally arbitrary. It's not totally arbitrary. So on a given subset, we need to justify the Lipschitz embedding exists. The Lipschitz embedding exists. Just think of the case. If I'm going to pick n points in the subspace, which is the null space of A, all the points will be mapped to 0. In which case we cannot realize the near isometric embedding. So that's something we need to keep at the back of our mind. Johnson-Renton-Strauss lemma, we have already talked about that. The J lemma was proved in 1981 in pure mathematics literature. Let epsilon be greater than 0, n be an integer, be given. What is n? N is the number of data points. then for all integers k greater than or equal to k naught, which is log of n divided by epsilon square. The set of endpoints randomly selected in Rd, there exists a mapping Rd to Rk which satisfies the inequality 7, which tells you this is near isometric embedding for all u and v belonging to x. The f in the JL lemma is called the JL embedding. JL embedding. Please understand what is the statement of the theorem. There exists a mapping. JL did not give the lower bound on k. They simply said there exists a lower bound. It is the computer scientists who came after the publication of the JL lemma, which is called Johnson-Anderson's lemma, in the early 90s, within a span of a decade. It was very well understood within the computing community. The importance of that was well recognized. They started refining some of the claims. So they wanted to find out how small k can be. And what is the claim? The claim here is k has to be larger than of the order of log n over O of log n over epsilon square. Now please understand, this bound is independent of capital D. It depends only on the number of points. It depends only on the number of points. That's a very interesting result for you to be able to notice at this time. JL did not give the lower bound on k. It was made clear subsequently that f can be realized using random projection, and various lower bounds on k were subsequently established. And I want to ask you to go back and reread the lemma once again. That for epsilon greater than 0 and n in integer given, for all integers k greater than or equal to log n over epsilon square, and a set n points randomly selected in Rn, there exists a mapping which satisfies this property. So they showed the existence of it. Then in computer science literature, they started giving life to the mapping. So the random projection based on Gaussian random variable is what we are now going to take up for the analysis. So what is the path we walked so far? I would like to be able to give you a very straightforward approach to the notion of designing near isometric embedding. In 1999, Dasgupta and Gupta, they wrote a very interesting paper. It's a very short paper, but it's a beautiful paper. For epsilon greater than 1 and an integer and an integer n greater than 0, let k be a positive integer such that k is greater than 4 times inverse of epsilon square by 2 minus epsilon q by 3 log n. Then any subset n of Rd with n points, there exists a linear map such that for all u and v, the near embedding can hold good. Now please understand, this is a probabilistic statement. So this is an event happening. So I need to be able to compute the probability of this event happening. So look at this now. If I took the ratio f of u minus f of v whole square divided by u minus v whole square is less than or equal to 1 plus epsilon and 1 minus epsilon. So that means there is 1, this is 1 plus epsilon, this is 1 minus epsilon. This ratio is a random variable because the numerator is random. So if the ratio lies greater than 1 over epsilon or less than 1 over epsilon, that's called tail event. So this is the desired interval. Outside of it is called tail. So in order to show that this happens with an overwhelmingly large probability, the trick is to show that the event does not lie in this interval, is going to be very small, and I can control the probability. That's the basic idea of the proof. Furthermore, this map can be found in random polynomial time. So those of you who are not introduced to complexity theory can be rest assured that this mapping, being a linear map, I can generate them. I can also apply this map to any vector, the times the computing the matrix vector product. They are all easy problems. So an algorithm has a, so for those of you who want to know a little bit about random polynomial time, an algorithm has a random polynomial time. If it runs in polynomial time in input size, and if the correct answer is no, it always turns out no, while the answer is yes, it returns yes with a very high probability. With a very high probability. So that's the idea. You may remember I have talked about Las Vegas type algorithm, Monte Carlo type algorithm. The Las Vegas type algorithm provides a no answer, but to get an yes answer, you may have to wait longer. So in that case, we are going to talk about expected number of rounds needed in electing the reader in a city. That we have already talked about. So something similar to that, that's the technical term, polynomial term. I hope you got the idea of what that polynomial term is all about. So what is that now we are going to have to indulge in? We simply need to be able to show that if the matrix R is designed in such a way that the elements are from IID, random variables from standard normal, we have already proved that the expected value of FFA, square of the norm, is the same as square of the norm of A. We now know there's a hope for being able to derive the concentration inequalities. So the rest of the dealings is going to be with deriving that tail probabilities. So I have a lemma. Now, some of you may know in mathematics, we sometimes use the word property. We use the word fact. We use the word theorem. We use the word lemma. So what is the difference between a theorem and a lemma? A theorem is generally a grand result. A lemma is also very nice result, may not be as grand as the theorem itself, but a sequence of lemmas relate to sequence of results that we need to apply to prove the theorem. So these are lemmas are a set of subsidiary results that we need to be able to produce in order to be able to pull together the proof of the original theorem. So you in a paper, you may not want to have too many theorems. You may want to have only few theorems talking about the major contributions, but you will have several lemmas, side kicks, the intermediate results, which are interesting in themselves. So lemma 2, let R be a k by d random matrix whose elements are type 1. Let A be a unit vector. Now I'm trying to restrict myself to a unit vector with a loss of generality. Y is equal to R times A. Now I'm going to look for I'm going to assume there is a constant beta, which will play a very important role. Then look at this now. What is Y? Y is the image of A under Y is the image of A under R. So A is a deterministic vector, Y is a random vector. I'm interested in the length of the square of the random vector. So k by beta, beta is greater than 1, so k by beta is a number which is less than k. Now look at this now. This is 0. This is called the norm of the vector y. Now I want to make sure the norm of the vector y could be anywhere, because norm of the vector, square of the norm of the vector y is a positive random variable. We know this is positive. So what is the probability that the square of the norm of y, the image of A, will be less than k by b? The probability of that event. We are going to show, the claim is that this probability is less than k by 2 times 1 minus 1 over beta minus log beta. Likewise, this is a non-zero random variable. What is the probability that it will be greater than k times beta? So look at this now. I will read out this to be able to bring you a better idea. Here is 0. Here is k by beta. There is k times beta. So I'm interested in the probability it lies above and lies below. Please understand, this can never be less than 0. So if I can compute these probabilities, if I add the probabilities of these two events and subtract it from 1, that will give you the probability that lies in this region. So the probability that lies in the desired region is 1 minus the sum of the probabilities of the two tails. This is where the tail distribution comes in very handy. And these probabilities are upper bounded by exponential functions. You could readily now have an idea that exponential bounds are general results of Chernoff type inequality. So these are related to the concentration results, measure concentration. First, let us take this lemma, assume this lemma is for granted, and use it to prove the theorem 1. Please understand, as I told you, the lemmas are intermediate results that helps you to be able to build the results of the original theorem. So I need to be able to prove the lemma, but let me take it for granted. Let's indulge in the use of this lemma in proving the major result. And once we do that, we'll come back to proving the lemma 2. So I'm assuming lemma 1 is true. Lemma 2 is true. So theorem. Recall all is a k by d matrix from IID from 0, 1. U and V belong to X are two distinct elements of X. I have a unit vector A which can be realized as U minus V by length of U minus V. F of A is 1 over K RA. So if I call Z a random vector F of A and Y is equal to square root of times K times Z, so Z relates to Y and Y is RA, which we already know. Then square the norm of Z, square the norm of F of A, which is equal to F of A being realized as the normalized difference, and which is equal to 1 over square root of K R times that. Now you should know A times, if G is a vector and A is a constant, A times Z is equal to 1 over A times G. You should all know that. Therefore, and it is square the norm. So the norm of U minus V whole square K comes out. I'm taking all the constants out of the square of the norm. R times U minus V is the remaining term. F of U is 1 over K RU. F of V is 1 over square root of K RV. Therefore, F of U minus F of V is 1 over square root of K RU minus V. Therefore, equality 12 follows. Now, combining 11 and 12, which is pretty straightforward, you now see the norm of the square of Z is the same as the norm of the square of F of U minus F of V divided by U minus V whole square. So I hope you are all with me in this sequence of results. So this is the ratio we're interested. I want this ratio to be upper bounded by upper bounded by 1 plus epsilon and lower bounded by 1 minus epsilon. So look at this now. This is 1. This is 1 plus epsilon. This is 1 minus epsilon. So what is that we are asking? The ratio being less than 1 minus epsilon. What is the probability of that? And this ratio is the same as the square of the norm of that, which in terms of Y is equal to K times 1 minus epsilon, square of the norm of that. Likewise, please verify the complement of that this ratio is going to be greater than 1 plus epsilon, and that becomes norm of y square is greater than or equal to k times 1 plus epsilon. Now, if we set 1 by beta is equal to 1 minus epsilon in lemma 2, and we apply the right hand side of 14, we get using 9. So there are lots of little things that's going on in here. I want you to be able to, so this is simply applying the results of the lemma appropriately, choosing the parameters. So y square less than this. From the lemma, now I'm going to get this upper bound. I hope you are with me. This is from lemma. Log 1 plus x has an expansion. Log 1 minus x has an expansion. So apply this expansion to the exponent on the right hand side of 16. Please understand, I don't want to read every little thing I have written, but they are all very clearly written, so you should be able to go over that and check everything. So apply to the exponent on the right hand side of f in 16. If you simplify that, that becomes minus epsilon square by 2, and that essentially tells you the probability that y square is less than or equal to 1 minus epsilon times k is exponential times minus k epsilon square by 2. Now set beta is equal to 1 plus epsilon in lemma 2. Please understand, the lemma 2 is the key here, and apply the right hand side of 15, and you already know what 15 is. Let's go back and check it out. This is the ratio. This is 15, and that's a key result that we have already seen. So set beta is equal to 1 plus epsilon in lemma 2 and apply it to the right hand side. So the probability of the ratio z square is greater than 1 plus epsilon is equal to the probability that norm of y square, the square of the norm of y greater than or equal to k times 1 plus epsilon is less than that. Again, I'm going to have to expand logarithmic series. I'm sure you all know the expansion for logarithmic series, which I have been using. So I'm now going to manipulate the exponential term, the index of the exponent term, combining 20 to 22. All these things are simple calculations, which I believe you should be able to verify. And that's going to be part of the homework for you to be able to check. I know you are all going to be master student. If there is anything that should not bother you is algebra. Therefore, probability that y square is greater than or equal to k times 1 plus epsilon is equal to is upper bounded by exponential of minus k by 2 times that. Now, in 19, I got one inequality. In 23, I got another inequality. In 19, I got this exponent. In 23, I got this exponent. So I have two exponents. I want to find out which one dominates the other. So if this is greater than that, minus epsilon k by 2 epsilon square will be less than that. That means exponential minus k by 2 epsilon square will be less than that. Now, knowing which one is, see, this is one bound we got, this is another bound we got. This bound is less than that. So I would like to be able to control the upper bound, the larger the two bounds. So this is the larger of the two bound. I'm going to require set that let this bound be less than or equal to exponential minus 2 times log n. This inequality 25 is true when the exponents and the exponent are related. So when this is related like this inequality will be true. The inequality in 25 will be true. Now we already know that if a is less than b, minus a is greater than minus b. So k by 2 is k by 2 times epsilon square by 2 minus epsilon q by 3 must be greater than or equal to 2 log n. That essentially tells you my k must be greater than or equal to 4 log n divided by epsilon square by 2 minus epsilon q by 3. This applies to 20 and 23 simultaneously. So when k satisfies 26, that's a lower bound. What is k? K is the dimension of the space into which I am going to embed. So the dimension of the receiving space must be at least as large as 4 log n divided by a polynomial in epsilon. If k satisfies 26, you can readily see exponential this is equal to 1 over n square, is 1 over n square. So by 24, this bound applies to the right hand side of 19 and 23. Hence, from 19 and 23, we get that probability that this happens is less than this, probability this happens is less than this. So these are two things I would like you to be able to look at this now. This is 1, this is 1 plus epsilon, this is 1 minus epsilon. In one case, I talk about this tail, another case, I talk about this tail. These are two independent tails. There's a theorem in probability theory that probability of the union of A and B is less than or equal to probability of A plus probability of B. So by applying that, the probability that the ratio does not lie in here, does not lie in here means what? It lies outside of that. Does not lie in here. Outside of that is sum of the two. Is sum of the two by applying this rule. Now, we do know what is y square. Y square by k is essentially f of u minus the square of the norm of the difference in the images. So the square of the norm of the f of u minus f of v divided by u minus v. So we get for each pair uv, u not equal to v, that 1 minus epsilon, the desired inequality holds with a probability at least 1 minus 2 by n squared. 1 minus 2 by n squared. So that's a concentration inequality. That's a concentration inequality. So what does it mean? With a very high probability, if you design your function f the way we have, you will get near isometric embedding. So that's a claim of that. Now there is the details of the proof of lemma 2. I'm not going to go over the entire results of proving this. I'm going to show you the major steps. So everything has been done based on the lemma 2. So lemma 2 is going to bear the responsibility of the theorem being true. So lemma 2 has 2 bounds. The proof of these 2 bounds is now picked up in here. So I'm now going to go to this event. I'm going to be using Markov inequality. The Markov inequality gives rise to this expression. I want to be able to compute y is equal to Ra, yi is equal to that, the linear combination of Raj. So Raj are IIDs of Raj's are IID standard normal. So E of yi is 0, the variance is 1, we already note that. So yi, okay, now look at this now. Yi's are linear combinations of normal random variable. We all know linear combination of normal random variable is also normal. Until now, we used only the first moment, second moment. Now we are also trying to pin down the distribution of yi. So yi is normal. This is an important conclusion. Yi transpose, that is the total variance, that is equal to k. So expected value of minus hyi square, yi square, yi's are essentially normally distributed. So this is the normal distribution along with the quantity. I'm taking the expected value of that. So what is this? This is the moment generating function for the random variable minus HYI square. I'm computing the moment generating function for the normal random variable, for the square of the normal random variable. I'm now going to show you all the calculations in page 14. These are standard one. Combining 30, 31, 32, I'm going to get the collection. So look at this now. What is that we have shown? The moment generating function for minus HYI square is 1 over 1 by 1 plus 1 over square root of 1 plus 2h. YI square are the components of the square of the norm. So by applying the individual results, because YIs are all independent, its moment generating function is simply the product of that. Now please remember, YIs are vectors in dimension k. So this expression comes from the earlier consideration. Therefore, the moment generating function for minus h times the square of the length of y is given by this. If I get the moment generating function by applying the Chernoff bound, there is going to be a parameter. In this case, the parameter is h. I can optimize the parameter by trying to minimize h, and so g of h has this particular form. I'm trying to minimize g of h, find the value of h for which the g of is minimum. The h star that minimizes is beta minus 1 by 2. Therefore, g of h star is beta to the power minus k by 2 exponential k by 2 times 1 minus beta, which is given in 35. Now, we all know a is equal to e to the power of log n a for any a greater than 0. So, by applying this, beta to the power minus k by 2 is simply e to the power of minus k by 2 log beta. Substituting 37 and 35, we already know gh star is given by this, which when substituted gets simplified to that. The minimum value of the right hand side of 30 is given by 38. So this is the minimum value of that, which is the claim 9 in lemma 2. So lemma 2 can be verified using simply doing two steps. One is trying to apply Markov inequality, and then trying to compute the moment generating function and try to minimize the upper bound and the moment generating function by appropriate choice of the parameter parameter h, so that you get the best upper bound. So we now consider the complementary inequality, which is again follows the same idea. By again Markov inequality comes in here. The methodology essentially is the same. I want to show you the pathway so that understanding these pathways, doing these computations is going to give you skills that you can exploit in other application areas. So if you verify the above argument, that by the same argument that led to the previous one, you can now verify the moment generating function for the square of the ith component is given by 1 over 1 minus 2h. If you extend that to the whole vector, it becomes 1 minus 2h times minus k by 2. Same principle, you get the bound, upper bound. I have a function, this is a function of h. H is a free parameter. I'm going to identify gh, and gh attains its minimum value, which is at h star is equal to b minus 1 by 2 beta minus 1 by 2 beta. Gh star, so the optimal value is given by this, and that gives rise to 41, which in turn helps you to prove 10. So we have now proved the entire result. So in summary, what is it we have done? we have tried to approach the notion of dimension reduction using random projection from a much more basic way without having to resort to other results. So this is probably proof that anybody who has done reasonably good probability theory course can understand. I would consider this an elementary proof for dimension reduction to get the bound on, to get a lower bound on the number k, which is the required dimension to achieve the near isometry. So what does it say? In order to be able to get near isometry, your k cannot be too low, and that should not be a surprise, because we have already talked about embedding from two-dimensional space to one-dimensional space. So if I have an equilateral triangle in a two-dimensional space, if I try to map it to one-dimensional space, you cannot get even near isometric embedding. We have already talked about that. That means the receiving space must be large enough to be able to accommodate near isometry, and that how large is large enough? It is lower bounded by log n divided by a function of epsilon, generally a function of epsilon square. So with that, we now conclude the elementary proof for the Johnson-Lindenstrauss theorem, which is the major theorem in data science relating to randomized approach for dimension reduction. Thank you.